Hello everybody, welcome to the latest edition of the Physics Corner. I'm your host, Dr. Christopher Cirola. Today we're taking a look at the image you get by sending light through a converging lens. Specifically, I'll have an object some 7.5 centimeters in front of a converging spherical lens that has a focal length of 5 centimeters. We want to find out where the image is going to be located and the magnification of the image, and then address the question whether the image is a real image or a virtual image. Now I'm going to solve this in two different fashions. One fashion is straight up old-fashioned equations. We'll go ahead and calculate the numbers we need to calculate. But I also wanted to do a graphical solution. In other words, sketching the solution. And while the sketch is going to be freehand and won't give you precise numbers like you might desire, it will give us a good sense as to what the solution should literally look like, what kind of things you can expect to get. And let's see if we do a good enough job to have those agree with each other. So the knowns are the object distance and the focal length. So this, by the way, deserves its own comment very quickly. Some textbooks use SO, that's an O, not a zero in this case, SO as a symbol for object distance, S being a symbol that we sometimes use for distances. That isn't a standard, unfortunately, in the physics world. There's several different versions of that. Another popular one would be the letter P, for example, stand for object distance. Some people use just O, the letter O for object distance, and so on. So if you go looking at other resources, textbooks, online, you may find object distance as a different symbol. Similarly for image distance in the same comment, SI, image distance there. But again, you might find Q, so P and Q, of course, or you might find I for image distance, and so on and so forth. So unfortunately, there's not a standardized set of symbols for these things. We usually do a better job of it, but for some reason that's never happened. On the other hand, focal length almost always guaranteed to be F for focal length. So one comment along those lines, as we often say, the letter is used for several different things, like F for friction or F for frequency. Here, the little letter F is now a focal length. But it's all in context, right? You're not going to get this confused with, say, friction. There's no friction to talk about in this problem, right? So, but that is always worth mentioning. And similar comment here, little letter M. Sometimes you'll see a capital M. It's usually a little letter M for what we call magnification. We'll talk about magnification, how to calculate that, what it means as we go along. But also, little m is used for mass, it's used for meters. Here, as you will no doubt recognize, again, it's context-driven, m for magnification in our examples here. So before I sketch the picture, let's do a calculation, right? So if I want to calculate where the image is going to land, that's SI, the formula that we use is this. 1 over F equals 1 over SO plus 1 over SI, like this. Now, I want to take a little bit of time to show you how to solve for SI here, because this is a formula that uses several reciprocals, if you will, right? Reciprocals of F, SO, and SI like that. And unless we're careful, it's easy to get this messed up. On the other hand, when I give you the solution, then you have the solution for all these kinds of cases. And this formula shows up for lenses of various types, whether they're converging or diverging. This will also be the same formula we use for spherical mirrors, turns out. Again, whether they're converging or diverging. And so it's very versatile, right? It's not quite as versatile as, say, Ohm's law, but it does show up in many places and has a good track record that way. So what we want to do is find SI, right? So to do the algebraic solution, let's subtract 1 over SO from both sides. And so 1 over SI equals 1 over F minus 1 over SO, like that. Okay, next thing is we can't subtract these things directly like this. We need to have them or make them common denominators. So in order to do that, we're going to leave 1 over SI by itself, take 1 over F, and multiply by the ratio SO over SO. Now, as we all know, when you do this, SO divided by SO doesn't really change anything, at least not the answers, because, of course, any number divided by itself is 1, right? So we're just simply transforming how we're going to look at it. Similarly, I'm going to take 1 over SO over here and multiply by F divided by F. Now, the rationale for doing this is, if you look carefully, FSO will show up on the bottom, right? It'll show up in the denominator. So we have a common denominator and we'll be able to move forward with it. So 1 over SI then equals SO over SOF, like that, minus F divided by SOF. And since I have the same denominator now in both cases, I can consolidate. SO minus F divided by SOF, like that. One more step for an algebraic solution. This isn't SI, this is 1 divided by SI, right? So flip everybody. So SI then, if I flip it, I have to flip this side as well. So SOF divided by SO minus F. And this is a pretty good common solution to know, right? So if I take this general formula and rearrange it for SI, I get that. So that comes in handy. All right, another thing to check while we're at it, SOF divided by SO minus F, if you look at the units, there's 2 length units here, 1 length unit on the bottom here. 2 length units cancels out one of them. A length on this side, a length on that side. Unit-wise, it also agrees. So we're in good shape there. All right, let's go ahead and throw in our numbers then. So we have 7.5 centimeters for SO and 5 centimeters for F, and then 7.5 minus 5, like that. Okay, so 7.5 times 5 is 37.5. 7.5 minus 5 is 2.5, like that. And we can check with the calculator to see what happens, but we end up getting 15. One of the centimeters on top cancels the centimeter bottom, so SI equals 15 centimeters. So that is our solution. So the image should show up 15 centimeters away. Now, to give you a quick preview of what the picture is doing, each of these little notches here represents 5 centimeters. So here's our focal length, for example. Our focal point is at that spot right there, for example. Here's our image, or excuse me, there's our object, sorry. And that means our image will end up being formed when we have light rays coming from this object, passing through this lens, and somewhere over here, 5, 10, 15, if you will, centimeters away, will be where the image shows up. Now, what's that image going to look like? That's the next calculation. That's magnification. Magnification is negative SI over SO, like this, okay? So, negative of 15 centimeters divided by SO, which is 7.5 centimeters. I think it's kind of easy to see. 15 divided by 7.5 is 2, and there's a negative sign. Now, a couple things about our solution. First off, no units. Centimeters cancel centimeters. So magnification is simply a ratio, right? Second thing, there's a negative sign. What does that mean? It means our image will be upside down. It will not be right side up. It'll be upside down compared to the orientation of the original object. One more comment to make. It didn't show up in this particular example, but magnification in common usage tends to mean make bigger, right? That's the point. If you magnify something, you make it larger. Not necessarily here. It is possible to have an idea or to have a calculation where your image is actually smaller than the original object. As an example from everyday life, take a look at, say, or think about the image of a car in your rear view mirror. That is definitely smaller looking than the actual car you're looking at behind you, right? So it's possible to have images that are smaller than the actual object is. It didn't happen in this case, but it is possible. So magnification is simply a ratio of sizes. It's not automatically bigger. It doesn't have to be. All right, so those are our algebra solutions. What I'd like to do next is a graphical solution. And how do we do that? Well, there's a couple of shortcuts for this kind of thing. Let me show you. One is, what is the definition of a focal length in the first place? The definition of focal length is that when you have a ray that's parallel to the normal, and in case it's not obvious, this line I've drawn across the middle is a normal, right? It's perpendicular to the plane of the lens. So that's a normal line, right? Normal line going right through the middle of our lens. If we draw a parallel line to the normal, and I can do that like this, so there's a ray of light, if you will, coming from the head or top of our object to the lens, that parallel ray will be bent directly through the focal point. And so if I line this up carefully, all right, something like this, my exiting ray, my ray that goes through the lens, will look like that. All right, so that's one way. Now, there's a couple of different ways to go about doing this next line or ray. Okay, let me do it this way. One of the rays you can draw to help get you an image passes through the middle of the lens. By the way, one ray is not enough to get an image. I simply have a ray of light that's going off into the distance that doesn't tell me where the image is going to be. It just simply says that's one ray to get. The way to form an image, you need multiple rays, at least two. If you draw this enough, you can do more than two, but two is usually enough to get across the idea. A shortcut idea is to go straight through the middle of the lens. And these are what are called thin lenses in these formulas, which means a ray that passes directly through the middle of the lens is unaffected. It just simply goes through. It's thin enough that its direction is not changed. It's still going in the same direction that it was before, and so on and so forth. So let me do that. So I go again from the top of my object all the way through the middle of my lens, and I get a ray that does that. Okay. Now, by the way, I'm using the top of the object, and I've drawn a little arrowhead to stand for my object. Why am I doing that? Well, it's so that we can get an orientation for the object. If I just drew a sphere or a line segment, there wouldn't be a way to tell the orientation of the image compared to the original object. So I want to know what side's what. That's why we're doing it that way. All right, so if you notice, the rays come together here, and then they split apart again. That's where the head of the image will be located. But notice that the image is below, not above, but below the original normal. So our image will look like this. And let's see how well we did. Pretty well, I think. So if each of these notches in my picture represent 5 centimeters, okay, so if you notice this is 7.5 centimeters off to the left of here, then if I go 5, 10, 15, I'm almost exactly at the 15 centimeter mark. And we said our magnification is twice that of the original object. So I have 1 line's worth going up like this for my object, 1, 2 to get my image. And so the image is twice as large as the object, and the image is pointing upside down compared to the original object. So all those hold together. All right. One last bit to talk about, and that was this last question: is the image real or virtual? Now, I don't know why it's gotten written that way. It should be virtual here. So virtual. His brain is going ahead a little bit. So image is real or virtual. What does that mean? A real image is when the actual physical rays themselves meet up and create an image. And that does in fact happen. A ray travels through the lens, goes all the way over here. Another ray physically travels through the lens, goes here, they meet. Which is to say that if you had, say, a lens like this, and there was an object 7.5 centimeters in front of the lens, on the other side of the lens, if you put your eyeball right there, you would see a focused image. That's what you would see. You could literally go to that place, at least in theory, put yourself there, put your eyeball there, or a camera or some other instrument, and actually get the image. And so this is a real image. One more bit before we go. For lenses, we're always in front of a lens for an original object. So if I put an object, by definition, it's always in front. It's a pretty standard move to put it to the left of the original lens like that. Okay, so the lens is here, our object is here. being on that side of the lens is a positive object distance. What about the focal length? Is it possible to have a negative focal length? And it is for diverging lenses. That we'll do that in a separate video. This particular video, we're using a converging lens with a razor bent inwards, and so the focal length is here, or the focal point is here, and the focal length from the middle of the lens to that spot is that. Notice that I've got that on the opposite side from the object. Why is that the case? Well, because the job of a lens is to bend light. Light passes through a lens, right? So if we have the light bending through it, then that focal position, if that's on the opposite side of the lens, because the light rays pass through it, that is what we call, by convention, a positive focal length. And similarly for the image, if the image is on the opposite side of the lens from the object, object's here, image is over here, again, that's a positive image distance. So this distance from here is positive, and in fact, that is what we calculated. Okay. So a little bit of work on that. Now, in future videos or different videos, we'll show some other examples. We'll do the same task, right? We'll go ahead and calculate, and we'll sketch with the same sort of ideas and show us how to handle a few different kinds of orientations or examples, different lenses, different positions, and so on and so forth, to get a feel for what that might look like, both in terms of calculations and in terms of your pictures. All right. Our technical support is Sidney Galtra and Sophia Turner. Funding for our programs comes from the University of Mississippi and University of Southern Mississippi. We shoot these videos in Hattiesburg, Mississippi. I'm your host, Dr. Christopher Sorolla. As always, thanking everybody for their attention and clear skies.